All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap. Okay, so this is a follow-up on my videos to divisibility test. I was hoping those would give you sufficient motivation to maybe be interested in what modular arithmetic is. In this video, I'm going to talk some more about modular arithmetic, what makes it work, give you kind of a skeletal idea of the underpinnings of it. And then, show you one application of beyond the divisibility test, why we do it. So, there's a lot more to it than I can even get started on. Okay, we're going to start off with something that you may very well be familiar with. And even if you aren't familiar with it, it's not difficult. We're just talking about it now so that we can have some precise language about it. The idea is we start off with two integers, a and b. We're going to say that b divides a if there is another integer n such that a is equal to b times n. And in this case, we write that b vertical mark a, and we will read this as b divides a. And so you're doing integer division, but there's no remainder left. This b divides a with no remainder, divides it into an equal number of integer-sized pieces. Okay. Now, there's some basic facts that we're going to want to use with this. If we have integers a and then a1, a2, b, and c. If b divides a1 and b divides a2, then b will divide a1 plus a2. Okay, so this is like 3 divides both 6 and 9, so we know automatically without doing anything that 3 divides 15, which is 6 plus 9. Okay. And the second bit, if b divides a, then b divides a times c, where again c is any integer. And so this is pretty easy to see. What I'm going to use this for mainly is that if b divides a1 and b divides a2, then b will divide a1 times a2. But we get more if we state it this way. We get a little bit more. Okay, now we're going to introduce you to the concept of equivalence modulo n. Okay, so here we're starting with n, an integer, but we want to restrict ourselves to n just being a positive integer. Let a and b be integers, and they need not be just positive integers. They are just any kind of integers. We say that a is equivalent to b modulo n if n divides the difference between a and b. Okay, so you take their difference. If that's divided by n, then they're equal modulo n. Okay, and so in this case we write that a equals b mod n. And since it's more compact, and I'm going to be doing this a bit, I'm going to say a triple line equals sub n of b. And this is, we'll read them, but this is a is equivalent to b mod n. We say them the same way. So this is quicker to write. Okay. Some things we know about equivalence mod n. So again, we got n, just pick a positive integer. We pick integers a, b, and c. They're just integers. A is equivalent to itself mod n. Okay. if A is equivalent to B, then mod n, then B is equivalent to A. Okay. So it doesn't matter which order you have them around the equal sign. If A is equivalent to B and B is equivalent to C, then A is equivalent to C. So they're reflexive. Okay, that's what one is called. Equivalence mod n is reflexive. Part 2 is called equivalence mod n is symmetric. And part 3 is equivalence mod n is transitive. Okay, so given these three things, equivalence mod n is what we call an equivalence relation. Okay, and so this gives us some powerful stuff that we can use. And here at the end, and I want to be careful because it would be easy just to forget it because it's not numbered. If r is an integer so that a is equal to b times n plus r, then a is equivalent to r mod n. So if we divide a by n and it leaves r as a remainder, then a and r are equal mod n. So what we wind up doing a lot is when we have an integer and are thinking mod n, then we will just divide it by n and keep the remainder, and we'll be able to use that remainder for whatever we do thereafter. And usually the arithmetic will be easier for us. Okay, we're finally getting to the point of all of this, the modular arithmetic. And suppose we have A prime, B and B prime, B integers. And we're choosing our notation so that A is equivalent to A prime mod n, and that B is equivalent to B prime mod n. Okay. Then if we add A plus B, then it's going to be equivalent mod n to A prime plus B prime. And if we multiply A times B, it's going to be equivalent to A prime B prime mod n. And so this, combined with the fact that all we really need is the remainder anyway, will give us some quick ways to use modular arithmetic. We can do this modular arithmetic, the sort of stuff that we've been doing to show our division tests. It does make sense, and we can do it. Now, let me just take some time to do some quick proofs here. To prove the first one, note that when I say A is equivalent to A prime mod n, that's just saying that n divides A minus A prime, and the same for B and B prime. All right. So since n divides A minus A prime and B minus B prime, it'll divide their sum. I can then just use the rules of ordinary arithmetic to reorder these and get that n then divides the difference between A plus B and A prime plus B prime. That means that A plus B is equivalent mod n to A prime plus B prime. Okay. For 2, it's just as easy. If A is equivalent to A prime mod n, that means that n is going to divide A minus A prime times B. Okay, so and since B is equivalent to B prime mod n, then n divides A prime times B minus A. This is not difficult to see. I mean, the n divides A minus A prime and B minus B prime, so if you multiply by an integer there, it still divides. Okay, so now let's take the difference between A, B, and a prime b prime. Okay, well, I add a 0 there, which means I subtract a prime b and then add a prime b back. Okay, so I've just added a 0. I can then factor a b out of the first pair and factor an a prime out of the second pair. And so, hey, n divides the first term, n divides the second term, therefore n divides the sum of the two terms. So n divides ab minus a prime b prime. Therefore, ab is equivalent mod n to a prime b prime. Okay, so how we carry this out in practice, we'll fix a number n. Here I'm going to just say n equals 4. And so then as we've said, we only really need to worry about the remainders of numbers divided by 4. So any remainder of a number divided by 4 is going to be 0, 1, 2, and 3. So I have a little addition table I've set up here, okay, with a summand across the top and a summand down the side. 0 plus 0 is 0, and in fact, you add 0 to anything, you get that thing back, okay. You add 1 to something, you just shift it over. The only interesting thing that happens here, 1 plus 3 is equal to 4. 4 is equal to 0 mod 4, okay? We could have put a 4 down there, it still would have been true, but the practice is to simplify to the smallest positive number that makes it true. Again, because it keeps the arithmetic simple. We can take, say, 2 plus 3 is 5. 5 divided by 4 leaves a remainder of 1. So 2 plus 3 is equal to 1. We can have 3 plus 3 is equal to 6. 6 divided by 4 leaves a remainder of 2. And that works in any of those. We do the same with our multiplication table. 0 times anything is still 0. If I take 2 times 3, that's 6. And 6 divided by 4 leaves a remainder of 2. 3 times 3 is 8. Is 9. 9 divided by 4 leaves a remainder of 1. There we go. And so you set this up. And there's nothing magical about 4. Okay. Any number, 2, 3, 4, 5, 6, 7, 8, any positive integer, this will work for. Okay. Okay, I'm going to give an application here that I think is pretty cool. I'm going to use this modular arithmetic to show that 127 is prime without really doing very much division. I'm going to start out, and what do we have to do? Well, we have to say that, show that this isn't any divisible by any prime number that is less than the square root of 127. And so 11 squared is 121, 13 squared is 169, so and 12 squared is 144. So basically check whether this is divisible by the prime numbers that are less than or equal to 11. And so we start at 127 modulo 2. Well, it's equivalent to 1 modulo 2 because it's an odd number. Okay. 127, what's it equivalent to? Modulo 3. Well, okay, there's a lot of ways to do this. One of which is like it's 120 plus 12. 120 is equal to 0 mod 3. So this is 7. Okay, 120 plus 7, I should have said. And 7 modulo 3 is equal to 1. Okay, so it's not evenly divisible. 127 modulo 5. Well, again, it leaves a 2 when we divide it mod 5, just because, you know, it's easy to see that. 2. Okay, you could, again, break it down to 120 plus 7. 120 is equal to 0 mod 5. Then 7 divided by 5 leaves a remainder of 2. 127 mod 7. Well, let's see here. I'll say that this is equal to 120, okay, plus 7, so that's mod 7, that's, so I can say it's 120, right, 120 is equal to 70 plus 50. The 70 is equal to 0 mod 7, so this is equal to 50 mod 7, which is equal to 49 plus 1. 49 is equal to 0 mod 7, so this is equal to 1 mod 7. So it's not divisible by 7. Okay, now 2, 3, 5, 7. Okay, how about 11 now? 127 mod 7. Okay, well, I've already done 7. Mod 11. So this would be 110 plus 17 mod 11. That's 17 mod 11. That's 6 mod 11, which isn't 0. So 127 isn't divisible by any of the primes which are less than or equal to 11. Therefore, it's a prime number. And we didn't really do any dividing. Okay. Well, I hope that you enjoyed this video, and at least it made you curious about modular arithmetic. It is interesting stuff, and as I said, there's a lot more to it than I could even begin to talk about today. But I hope it kind of whetted your appetite. If you like this, please give us a thumbs up and maybe throw caution to the wind and subscribe to the channel. Thank you very much. Bye-bye. Yeah, who is it? No, I'm not doing anything. Come on in.